Hey there, welcome back. Jeff Clark is here, and that's me. And I'm going to continue on in a topic called exponential functions. This could be found in an advanced algebra class, intermediate algebra class, or pre-calc, the analytic geometry kind of problems. So there's a lot of places, a lot of courses that exponential functions could actually be found. So whichever class that you're in, this will work. Now I'm going to work out of a packet that has some examples. And because this is being recorded, you can pause at any time and write down, copy down anything you need. So let's get started. Show you what I got. So unlike other functions you may have seen, for instance, linear, polynomial, rational functions, I think I've told some of you, or if you've seen some of my other videos, that the domain of any function normally is going to be all real numbers unless you see fractions, variables in the denominator. That doesn't have fractions in the denominator. The variable is in the power. Fractions, roots, there's no roots here. Logarithms, not there yet. And inverse trig functions, Those are the typical ones that I'd be showing in a, say, pre-calculus class. So since this doesn't have any of those problems, then the domain would be all real numbers. Okay, to be exponential, the base. Sometimes we call this the base. This is the base. It holds the power. The base has to be a positive real number, and it also has to be not 1, or not even 0, because that would be weird. Not 1, not 0. Those are weird. So any other number that's positive, 0 is not positive, of course. So any number that's greater than 0, you eliminate 1, then you'll get a behavior that either looks like this or like this. This is exponential, like growth. This is exponential decline. Sometimes carbon dating can be attributed to that. Savings accounts, yeah, that would be a good thing. You want your savings accounts to grow like this. You don't want your debt to grow like this. You don't want that. The national debt is this way, maybe even steeper. It's not good. So there's illustrations, good applications with regards to exponential functions. An example I might have here to try is y equals 3 to the x. And if it's a function, you could actually have f of x is equal to 3 to the x, of course. So using my technology, and then I'll take a look at the table down here. Using my technology, y equals 3 to the x, and then do zoom standard. You get a picture that kind of felt like the other pictures on the previous page. Now on the technology, it appears it stops right there, but it does not. It does not. And as you can see, a table of values, second table of values, if I continue to the left on the number line, see how the y values, it does not stop. Oh, and what's that? That's considered to be scientific notation right there. This is the same as -7 times 4.6 times 10 not -7. That would be 4.6. That was silly of me. That would be that'd be -7 comma negative 4.6 times 10 to the -4th power. -4th. It's called scientific notation. So if I took the decimal that's right here and moved it to the left 4 places, your decimal answer is around point. It's about that much, so it's kind of small, close to the x-axis. The y value is very close to 0. So the picture that you see right here doesn't stop. It should continue forever along the the x-axis like this. Same with this. Should go forever. So by the look of it, its domain's all real numbers. You don't exclude anything. There's no value of x that would cause the table of value to be like an error or undefined. And table of values would indicate as well what these values were on my table right here. So again, if you did a graph that's like this, 0, 1 is right here, and the graph is falling, getting infinitely close to the x-axis. So the domain would be all real numbers. D for the domain, all real numbers. However, the range, R for range, isn't all real numbers, and it appears that it's going to be infinitesimally close to 0. So parentheses 0, and it grows forever big. So that would be the domain and range. And these next pages kind of indicate sometimes you can plot some points, like plot, plot, plot. In your graphing calculator, might look like it's real close because it's hard to plot this value. You connect the dots, you might be apt to believe it's this way. That's very sloppy, by the way, not good. Don't do that. It also maybe looks like it stops in the graphing calculator. Of course, it doesn't. This is the best picture, and matter of fact, even better would be have it arrows indicating it's going forever. And those of you that might have a different model than the one I had, sometimes the graphing calculators with the color screen helps, because you might see the like a red curve right above the black x-axis. So that helps as well. The 84 calculator one I have is crummy technology, pretty pixely. Okay, make a table of values. This feels like, instead of base 3, it's a base 2. I can do the same thing, y equals. So instead of base 3, it's a base 2. And if I make a table of values like this, let's say we do 4. Let's say we do 4. Graph it first. Kind of looks like the last one. If I do 4, table of values. Okay, that's a nice one. So it might be go 3, comma 8, and 2, comma 4, and 1, comma 2, and 0, comma 1. Those are nice. At least 4. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. 3, comma 8. 2, comma 4. 1, comma 2. Again, you're not going to just connect the dots. Don't do that. That's not correct. You want to make the arrow go this way, and then have this, don't stop on the x-axis, have this go forever this way. And that's not bad, x and y axis. So if I adjust the power up here, if I just adjust the power, y equals, and make that power to be x subtract 3, here, and make a table of values, of course. What's the graph, and how does that change with the first one above? How does it compare? And if I go graph here, Gosh, it looked like it was the same graph from the previous one. It just got pushed over to the right. And so the transformations that you may have learned might be a shift, right, 3 units. Shift right 3 units. And the domain is all real numbers no matter what. D for the domain, all real numbers. R for range. I take a look at the picture, the graph, and how low it looks like 0 again, but doesn't include 0, and how high, infinity. So 0 to infinity. And you can plot or graph that. You can plot values, I know you can, and connect the dots, but be careful. Make sure you have arrows going the proper direction to indicate infinitely y values are going infinite top, and the x values are going infinite, what is that, left, the way you're looking at it, left. This one here, if I made a table of values, x and y, I can just do this before my calculator. If I let x be 0, that's going to be 1 for sure. Now, if I let x be 1, that would be a half. Oh, and if x was 2, that's 1/2 squared, which is a fourth. Don't be afraid of like -1, though. If you put in -1, you're going to end up getting the reciprocal, which is 2. So the picture should look like this. 0, 1, 1, half, 2, even closer, and -1, 2. It looks like there's like this little reflection going on from the previous one when the base is a fraction. And when you put that in your calculator and make that say 0.5, yeah, that looks good. Oh, I want to make that x. Okay, so get rid of that. 0.5 raised to the x, hit that graph, and does the picture look like this one? It does. It does. And again, the domain is all real numbers, and the range is the same as the previous one. Now this one here, you can't put this in the graphing calculator because the only way we can do with the graphing calculator that I have is if y is by itself, and I have no way of getting y downstairs. I have no way of doing it, solving for y as of right now. So the best I can do, maybe make a table of values. Eventually, we're going to wonder if it's a function. Now, remember, a function is passes the vertical line test, or for every input, there's exactly one output. So to answer the domain and range, I want to see if it's even a function first, but I have to plot points because I don't know how to get the y by itself if it is a function. So if I let's let y be something like y is 0, then x is 1. And if y is 2, okay, that's 4. How about -1? That's a half. Do one more. How about y is 3? If y is 3, that's 8 there. So 1, 0, 1, 0, be right here. 4, 2. Okay, a half, x is a half, and it's -1. So it's like right about there. And 8, 3. Okay, plotted those 4 points. Now if I connect the dots, of course you know you're not going to stop. You'd feel like probably this is going forever to the right, probably, and that's true. It looks like it stops, but it doesn't. It actually turns this way. And we'll find out in the next section, the next logarithms, you'll find out there's a relationship with this picture and the previous, one of the previous pictures, which would have been this one here. There's a relationship between this one, y equals 2 to the x, and this one, which looks like x equals 2 to the y. They're called inverses of each other, and we'll take a look at that later on again. So is it a function? It certainly looks like it. Looks like it. Looks like it. Okay, why? Then you'd say passes the vertical line test. Okay, what's the domain? Well, there's a blocker, there's a wall right here. The domain is in all real numbers in this one. So it looks like, what is that? X value is 0, but you can't use it, and it goes forever to the right. All the X values over here. So it appears that maybe that should be infinity, not 8. Silly me. Infinity. D for domain and R for range. That looks like it's all real numbers. That looks like it's all real numbers. Something about the E right here that I notice is called the natural number. The natural number. If you've never seen that before, just know that called the natural number. Like pi, it's a special symbol. Pi is a Greek letter of the alphabet, but it represents the number pi. Pi is the ratio of the circumference of a circle divided by its diameter. That's really what pi is. And some of you have memorized the first couple digits, 3.14, but be careful in your saying pi is 3.14 because that's not true. Grammatically, that's not true. You should say pi is around 3.14. Much better and correct. What's E then? If you look in your calculator, you look here, let's see. This is my calculator. Hard to see here. Well, one place is right here with this funny ln. That's an e to the x. There's an e. If I make that into a 1, power is 1. And if you go to the division symbol, right there's your pi. There's an e right there. That's the one I'm going to use and show you what e is. So for me, I have to press the blue button and then press the divide sign. And then notice I get e. I guess turn the calculator on. Do that again. Second E, and then hit enter, and there it is. It's a decimal approximation. No, there is no pattern. You might think it's 0.7118281828, but it goes on forever, and likely that 8 is something else that just got rounded. So we call it sometimes an irrational number. It's like pi is an irrational number. It's an example. Or transcendental number. So we like to call it in calculus. So we'll come back to E, called the natural number, in the next section or two as well. So all I'm doing here is I wonder about the transformations for that one and that one, for those first two. This one here, the subtract 3, would instead of the subtract 3 in the power, which I had on one of those problems, this is subtract 3 from the function 2x, 2 raised to the x. So this is going to be a shift down 3 units. This one here has 3 things going on, and it has to be a very specific order. The left right is always first. So if I did this, this would be a right. It's always opposite this. It's a right 1. So you might zoom in here. This would be a right 1. Second one would be the negative, which would be a reflection. It's a reflection around the x-axis. So you say reflect x-axis. And number 3 would be the 2, and that's up 2. So that's the transformation language that we've been learning, or you may have learned in a previous class, that when you compare this with the base function, y equals, just say e to the x, you compare those two, the picture here would be looking just like this, except it would be a shift of 1 unit. So it's a shift right, and there's a reflection upside down, and then eventually it goes back up by 2. And if you wanted to graph that, actually, just this right here, see what it looks like in general, negative e to the x. Okay, so that's x subtract 1. And I pop that down, and then plus 2. And then do zoom, standard 6. And here's the image. Kind of looks exponential, but it's upside down. Kind of looks exponential, but it's upside down. Okay, let's see. I'll let you graph this on your own. This one is very similar, identical, similar to that one, except it's a base 10. So you'd have to do a table of values on this one. So the only other one I want to look at in this section, it looks like this one word problem. I'd like to address this for now. The world population. Let's see, so many years after 1980. Now, if I look at the world population, let's see, what's the world population? I have 2016 here. Okay. The world population in 2016, and I'm going to show you this right now. Okay, so it looks like it was 2.4, 7.7 billion, a little over 7 billion, 7,426,000,000 people. If I wanted to go back and look at the graph, let's do 1900 to now. Yeah, let's do now. Let's see, where's my picture? Let's see what happens here. It shows the graph. Yeah, that's not a graph. That's just data. Let's do graph. Taking a look to see a particular graph, interactive graph. All right, let's see what happens here. I just Googled, of course you saw what I Googled. Let's see if this interactive graph actually comes up. Still waiting. Okay, now if you see what's happening right here, it looks like from what they can, maybe records, I don't know if they've got the records back then. If I look at maybe, here we go, getting closer, getting better. 1600. 1900 looks like it's growing exponentially, isn't it? So, so it looks like the growth of the world population is growing exponentially. Now, the year 2000 and 16, it appears to be, well, that's what we had, 7.46 billion people. I'm going to take a look at the formula that was given to you guys. Let me unshare this. Go back to my page and my, someone, I didn't, someone came up with this as I wonder if there's a formula that gets me close to that about 7.46 billion people. All you have to do is replace the t with how many years after 1980. And that looks like it's going to be 36 years. So t equals 36. And then you're in your calculator, you're going to put this in and make t be 36. Okay, it overshoots it by a couple million people, looks like. A couple 100 million people. It looks like it overshoots it. So it's not the best predictor, but in terms of the process, it's plug and chug, plug and chug. So for today, and in this video lecture, that's all I've got for you right now. The next time we'll take a look at its sister function, which is the logarithmic functions and how they relate to the exponential functions. So until next time, have a good day.